Ahmedabad. Hope, hope you had a nice lunch and the energy is pretty high. So I'll dive straight into the topic. So I will be speaking about something that we all fear the most in the coming days, AI and security. So I would be speaking on mind the autonomy, rethinking threat models in the AI age. A brief about myself. So as the host mentioned, so I was an open source committer with OpenDelight for some time. Then I started leading data platform for network analytics for enterprise networks at Cisco. And currently, I lead the distributed AI systems for the same network analytics team. So that's about me. And we'll dive straight into the topic. So what's the one word that probably you can make out of this mess? Anyone? The first word that you can see. OK. OK. That's good. Let's go to the next one. I'll make it a bit more interactive because post-lunch people tend to doze off. That's the experience with me. So I'll try and keep you a bit engaged. Where do you use AI? Anyone? In your day-to-day or in a job, where do you use AI? OK, projects, you're coding. What are the assistants that you know or that you make use of? Copilot. Yeah, Copilot is one of them. Gemini is the other one. OK. What are the issues that you face or that you are aware of? As in you face or your colleagues face, you face or your teammates face, something like that. Sorry? OK. Anything else? Context limiting. OK. Fine. Let's see. So we'll dive into the topic in 4 parts. So first, we will list down what are the security terminologies that you need to know of while you start analyzing and building up AI systems. So the security glossary is the first one. We'll look a bit deeper into how AI systems evolved over a period of time. So the evolution of the AI workflows, as it mentioned, the security vulnerabilities with specific case studies, and then how do I secure AI, the model and the tools that I have or that we all have to ensure that AI behaves the way that ideally we expect it to behave. And with security, it's a bit of a misnomer. Let's see why. So security glossary, I call it Namkaran because for anything that we start off, the naming itself is very, very important. Until and unless you get the naming and the terminologies correct, things don't stick to you. So we'll start off with that. The first one, what are vulnerabilities? So vulnerabilities are basically intentional or unintentional flaws within the system that basically allows you or the software to have bugs that can be exploited, right? So what are exploits or exploit kits? So exploits are basically the ways in which your specific vulnerabilities can be made use of. The exploit kit is a collection of exploits that basically can be used to attack a vulnerability within a software system. We have something called a zero-day exploit, as in vulnerabilities that can be exploited without even knowing that they exist in the system. What are CVEs? CVEs are common vulnerabilities and exposures. That's a naming terminology that basically people use to gauge the severity or the risk that is associated with a particular threat. And threat is a possibility of the system behaving or getting misused rather than working in the expected manner. So what is an attack surface? An attack surface basically refers to a series of points or methods by which we can actually attack the vulnerabilities, by which an unknown or an unauthorized person can gain access to the system, retrieve materials out of it, or carry out a cyber attack. That can be both physical as well as digital. An attack vector, on the other hand, is a specific entry point to the attack surface. So vector means direction, so a specific point in the attack surface by which an actor can make use of the systems via malware or a virus. Now, the next thing is trust boundaries. So when two systems interact with each other, there is a expected handshake that happens. So in the language of computer science, trust boundary is basically the invisible line between which two systems or two entities interact with each other. A data flow diagram is basically something that enlists the various trust boundaries within a given architecture so that we can figure out the attack surfaces, the various ways the system can be hacked, and what are the threats that it possibly has. Let us put it all together. So we have, so an exploit makes use of an exploit kit to target a vulnerability by injecting a malware or a virus. Now, let's do a simple exercise. So I have a code snippet. So if somebody could tell me what is the vulnerability in this particular piece of Python code. I expect most of you are developers, so this should be pretty easy. I'll give you 10 seconds more. If you want to answer, please raise your hands. Five more. Yeah, go ahead. Yeah. Can somebody has a mic, please? There. Can you please stand up at you, please?
Hello?
Yeah, go ahead.
So is it else if in the if age is greater than 18 and then the
no,
else
it's
if
even much
exists
before that.
Okay.
Yeah. Age more than 120, that's a contract scenario. So basically, I'll take that. So basically, the age digit is a problem, and the int of the value will be a problem. So imagine that, so age digit basically gives you whether it's a numerical value or not, given that there is at least one character within it. So imagine that user gives a Unicode character that somehow matches that age digit, but fails in the int value. So the int of the value will fail. It will throw up a value error, and it will pop up a denial of service. So rule number one, the vulnerabilities here would be the denial of service, and that because we are using the input as it without verifying it. So SQL attacks, cross-site scripting, authentication bypasses are the primary vulnerabilities that are exposed in this piece of code. What does that teach us? Do not consume or evaluate an input without validating it. So input validation and no input evaluation are something that we must do. And we shouldn't call external processes without being sure of what it can actually do. So in case you have a code that basically does an os.remove of a file, that's probably better than os of a system file, because if the file doesn't exist, you can end up killing the process. So now let's go inside a data flow diagram, the last nomenclature on that part. So this is basically how external prompt sources can typically interact with an LLM. So you have users, or via you can have APIs that basically asks LLM a question. So as we mentioned a couple of slides back, a trust boundary is basically the interface between which two entities talk to each other. So you have a trust boundary one, and you have LLMs interacting with either the private data sources, think of something as a RAG, or a vector database, or server-side functions. So basically, wherever two entities are interacting with each other, we have a trust boundary. So you have three trust boundaries here, 1, 2, and 3. Let's see what are the vulnerabilities that each of these trust boundaries expose. So the first trust boundary, if you see, that's between the users and the LLM. So that's the prompt. So prompt injection, you can modify the system prompt, you can modify the LLM parameters, the input, you can input sensitive information. So we have had people who input their PII, PHI information and ensure and expect the LLM to give some results out of it. It learns, and it can use it against you. Now, LLMs are unable to filter sensitive information. That's what we have seen. You can train them to. You can have guardrails around that, but currently they are not able to. So two major vulnerabilities in the trust boundary 2. So what was trust boundary 2? That's between the server-side functions and the LLM. That stick with us are the output controlled by the prompt input. So whatever the server-side functions, those come in, those are not controlled. You don't have a visibility or a control on what they do. And the server-side output can be fed back directly into the LLM, resulting in some kind of a server-side request forgery. So that's the vulnerabilities for 2. Now let's look at 3. So 3, again, it's an LLM to a private data source. So the first one still holds true, the output controlled by a prompt input, and the access to sensitive information. Now, your private data sources for most of the corporates can contain or will contain client information, PII, PHI, something that's very specific to the IPR that the company or the corporate controls. We need to be very, very sure of scrubbing or redacting all of them. Otherwise, we will end up with security vulnerabilities as exposing secret information. We'll look into more about that. So now, the evolution of AI workflows. So that's how we basically see or evaluate how a system, both from the code perspective or from a entire architecture perspective. Now, the evaluation of AI workflows, the past, future, and the present. So there's a little story behind it. So normally, I always ask people, how do you start with a simple system and try building features on top of it? So we had an intern, a bright one named Karthik. So we were looking at how can we automate the defect triaging process? Because the defect triaging process is pretty intensive. We need to have a lot of knowledge as to what the feature is, what the feature was, and what are the things that have been implemented or what are the things that are getting broken. So there are multiple knowledge sources that somebody needs to interact with to get to give a fix for that. So as part of his internship, the problem statement that he was given is automate that entire process so that we can bring down the manual intervention to a minimum one. So that was his problem statement. So the first pass that he did was, so he was the one who was recently out of college, so he knew LLMs much better than most of us. So he said, so there is an exception, null pointer exception for those who work with Java. I take that exception, I put it to an LLM, and I let the LLM answer. So null pointers was easy. There were some class not founds. It gave pretty good results, 40% accuracy, 35–40% accuracy. At least people with knowledge of the code would try and figure out where things went wrong or where things could go wrong. So that was his first pass. So a basic user asking an LLM a question or a prompt and getting the response, using that response to figure out where or in what places the things can break. So information retrieval is the first step. The next step was, so now that information still can be vague in multiple cases, because if you have customer issues which are open, things which have been fixed, things which have been broken over a period of time, that information varies. So what we said is, that is not good enough, Karthik. We'll have to look at a better way of attacking the same problem. So he went back, read about a bit, and he came back with the proposition of a knowledge base. So what did he do? He used the in-house databases that we have to index the entire architecture diagrams, the code, the presentations, bug information, and everything, and build a knowledge base out of that. So first, the query hits the knowledge base, gets some additional or enriched prompts out of it, and then it hits the LLM, gets the response, and it shows it. First part, it was brilliant, around 60 to 70% accuracy, and people were very much impressed with whatever he had delivered. So he made his presentation, and he got his internship done. So when he asked me for a review, I said, Karthik, mind the autonomy. So, and he has his normal way of asking, Shuva, what did you mean by that? I said, let's see. So he comes back. He comes back, joins as a full-time employee, and he starts picking up various left as an internship. Now, we need to improve that, because that knowledge base is static. Over a period of time, it can grow old. How do we ensure that the knowledge base moves with time? So now, he learned a bit more about things, and he came up with a re-ranking fundamental. What did we do? So we get the results, we figure out whether or how much of it is accurate, and we feed it back to the knowledge base and modify the knowledge base as and when we grow. So there's a feedback loop. That's part one. Part two is we put in a load balancer and then because we are from Cisco, so we put in the AAA, authentication, authorization, and accounting, so that the flow to the LLM is rate limited and it's authorized or secure. So those are the two pieces that he put in place. He put in a nice PPT, and he asked for feedback again. And I said, mind the autonomy, Karthik. And he still did not get it, what it meant. The next one. So now when MCP came in the picture by Anthropic in 2024, we wanted not to touch the knowledge base as far as possible. We wanted near real-time performance. What do we do? So for near real-time, we connected the knowledge bases. We had MCP servers, funky stuff. We created MCP clients, connected them. So you have Jira, we have our own bug databases, you have Git repositories. So everything has a MCP server. You just bring it in, you compose it, ask LLM a set of questions. LLM gives a nice, accurate, near accurate results. The accuracy increased to roughly around 80–90% on most of the cases. And it's working brilliantly. So he came back again, asked what's the feedback, and I told him the same thing. Karthik, mind the autonomy. Now this is the latest one. So with the advent of agents, we decided, why not get agents into the mixture? We have everything in. It's a potpourri. Let's get agents into the mixture. So beyond the API server, we have a orchestrating agent. And the orchestrating agent, basically what it does is, it tries and figure out from your local workspace, what are the things that you are possibly developing or looking at around the issue. It will collate that, hit the knowledge base with the tool's information, get a prompt, and ask LLM to specify questions on the Jira. So if I'm working on a Jira, I have figured out something. There is an automated process that will figure out what's the next step for it. And it's brilliant. It pushes the accuracy to close to 95–97%, even for the most difficult bugs. And again, he comes back and asks me the same question. The answer remains the same. Karthik, mind the autonomy. And he still did not get it. So we'll see why he did not get it and what is that I was asking him to mind. So case studies. Given that now we have seen how the workflows in AI has evolved, we'll look into two specific case studies that possibly show the extent of the severity to which things can go wrong in actual production scenarios, enterprise production scenarios. Enterprise production scenarios. Next one. Yeah. So drive-by localhost. Let's see. So there's a cartoon or a meme. So if you're just browsing a tech block with an MCP inspector running behind, for those who are not still catching up with MCP inspector, that's basically a tool that helps you to debug MCP servers, the connection between MCP clients and MCP servers. And it's a beautiful tool that helps you get bootstrapped on your local machine connecting to various MCP servers. So this says, so while we are trying to do that, why is my terminal running commands by itself? So while you are trying to develop something, somebody is already within your system trying to exploit it. You opened a website, and I accessed your system. So let's see what it is. So drive-by localhost is actually a new class of browser-based attacks, specifically for the AI developer tools in the MCP era. It's one of the first critical remote code execution errors or remote code execution vulnerabilities that have been exposed with a CVE score of 9.6. So that's basically, we graded out of 10. So you have threats, CVEs, and those are based on the risk and the potential harm that can cause. We give it a number. So it's 9.6. It's very, very high on the CVE scale. So if somebody hits it, your system is taken care of. So how does it do? It's one of the most critical, as I mentioned, most critical remote code execution flaws in Anthropic's MCP. It targets MCP Inspector. That's a debugging tool that connects or helps you to debug your connections with the MCP server. And how does it do it? So you have basically, in case you are browsing a web page that has a malicious JavaScript embedded into it. So by the time you are browsing a page and your MCP inspector is open, the JavaScript gets downloaded to your system, it runs, it figures out the port on which your MCP inspector is running, and it points it or it makes it to connect to an MCP server that doesn't exist. So there is a piece of code that it will have to redirect it to a program that can exfiltrate information out of your system. It can basically create backdoors for further damage via Trojans or viruses or malware. And the only way to prevent is isolation and better security. We'll see how. So the attack sequence would be a casual browsing, your malicious JavaScript execution on the web page that you have basically landed, the MCP inspector discovery by the software that's got downloaded, the HTTP endpoint exploitation of that MCP inspector. There's a tool called getting injected, and the system is compromised to ensure that things are run without your permission. So there's an access control violation that happens. Now, how do you prevent that, thwart that? So two policies, restrict access. So the first policy of security is principle of least privilege. You get to know if you are supposed to know. Restrict access and apply network isolation. Specifically, you containerize it, you limit the resources that it's allocated to it, and you monitor it and ensure that the local host is not exposed. So one of the primary reasons for the drive-by local host is how browsers interpret 0.0.0.0. So most of the browsers used to interpret 0.0 as a local host. So when there is a JavaScript that basically tries to incorporate non-coarse rules within it, it allows it to run without preventing it or stopping it. Restricted access, use firewalls or deploy behind an VPN or an authenticated proxy. For single client deployments, use STI transport. So for people who know how MCP works, you have both a streamable HTTP as well as STDIO. Use the STDIO transport for it. The next one is a supply chain attack, or basically attack via the jars or the libraries that we make use of while building AI systems. A meme or a cartoon again. So let's plug in the new MCP server. It should be safe because it's just using OAuth. Now, the OAuth endpoint or the MCP remote that the OAuth as a protocol is very exquisite. It's a beautiful protocol, but the problem lies in the way people have implemented it. So for MCP servers that don't have a built-in OAuth, we use an MCP remote as a front-ending or a proxy for authorizing it. More often than not, that version, so we had a vulnerability in the version 0.14 and beyond, previous. So that OAuth actually misbehaves. It will basically try to hijack the request that goes out of the client to the server and point it to a server that you do not know it exists. So I give it a shell access, and the OAuth is totally secure until you ask questions. So the moment you ask questions, it basically has a way to your system prompt, your local system, hijacking whatever you know of. So it's a remote code execution error again. It's a supply chain attack. It also has a very high CVE, around 8.2. What does it do? It basically gives vulnerability. It exposes the vulnerability within the inherent MCP process, exposing it to remote code execution errors. How do we prevent it? We'll see how. The attack sequence remains roughly the same. It's a legitimate setup. The OAuth discovery request goes through fine. You have the response is malicious, but you don't know that yet. And the code is executed on your system, and the system is compromised. The network isolation, your restricted access, and one important thing is secret management. So most of our, for local development, we use the .env file to store our API keys. So it's better that we use an IAM or a separate key management protocol to ensure that secrets are not stored locally in a system that can or potentially be compromised. Right? Now, most of you might think this is serious. Most of you might not yet. Why this is serious? Because most of the enterprises, when they started onboarding into MCP or the agentic architectures, we try and consume a lot of supply chain or third-party libraries that we assume is secure. So in security, there is a word that avoid security by obscurity. Just because you don't know doesn't mean it doesn't exist. It exists, but it's just that our knowledge is limited. So it's serious because most of the time when we are using code or when we are using something like agent, either it's a co-pilot or some agent that we're using to develop tools, push tools, we don't even know what's within it. And we inherently try or make ourselves much more, or our systems much more vulnerable than it actually is. So in the parlance of security, we have assets, we have the network, and assets on the network make a system. Now, so far, before the AI era, we had a full control on the assets that we had. The code that we ran on systems was something that we had developed. Yes, over a period of time, we started using supply chain things. We started using jars. So we have a way of figuring out, okay, what are the dependencies that we have. We check routinely for vulnerabilities within those dependencies, see what the vulnerabilities that have been declared, try and figure it out, do scans, regular, and then publish a report and get that approved. But with AI coming in, the dynamics changes. The dynamics changes primarily because of two different reasons. The first thing is we are pushing in code or we are pushing in features at a never before rate. We have seen development come down from years to weeks, but the security isn't catching up yet. So the amount, so we always say there is a requirement for the human in the loop, but there's always a physical or a limitation as to how much a human in the loop can do. If you are pushing in a million lines of code in a month, it's very difficult to figure out, or it's nearly impossible to figure out where things can go wrong. So that's why this has become so much important. So that was the reason when I told him, you are using the latest technology, that's good. You're building systems, you're trying to automate stuff that's mundane, but mind the autonomy. Mind the autonomy because of the fact that the autonomy pushes you to an extent, to a risk that you cannot foresee. And we have had situations on which the critical resources were on the line. Why? Now let's see the difference between traditional AI and agentic AI, past and the future, past and the present comparison. So it was pretty much reactive. Now it has gone proactive. So the current agents basically work on the SPAR principle. So you basically sense, plan, act, and then react back, right? So it's a full loop. So it can think on its own. That's what we see. It can think on its own. Supervision, there used to be a human in the loop, but with going time, we have agents that code on their own. Because they're running even on weekends, we produce more. But the most important part is that they are minimally supervised. Scope, it used to be task specific, very much categorized into what it can do, but it's now multi-step or more pervasive. It can do a whole lot of things, and it can take a whole lot of things out of your bucket. The interaction, it was contained and limited uses tools, because with MCP and multi-agentic architecture, you have given it access to everything. Your tools, your workflows, your databases, it has access to potentially everything that your organization has built up from scratch. Learning, it was static, and now it's continuous, adaptive, and evolves. So the core characteristics, autonomy, it has a goal-driven behavior. The tool usages and the libraries that it makes use of are pretty much advanced for most of the scanning tools to even catch up. There's a continuous learning that's required on the human side of the things, and it has a memory and a reasoning of its own that most often than not we are unable to figure out why, right? So agentic AI, practical examples, autonomous patching. What we developed was an autonomous bug triaging. So given a bug, it will try to figure out where all the error patterns are. Now with those error patterns and the knowledge that it has from the field, it will try to figure out where the possible patch could be. And based on that, it will use your own code base to push a patch to GitHub, fixing that and waiting for your review to finally get it merged. So that was the entire end-to-end process. So process optimization, it fits in there. Complex customer service, yeah. So debugging things, interacting with customers over long calls, they are pretty much put used to it. And the traditional threat modeling, so right from slide 1, the terminologies that we used. So you identify the assets, and you find out what can possibly go wrong. So there are multiple frameworks to do it. My personal favorite is Stride. Spoofing, then you would have, I'll come back to it. I can't recollect now. Then you rate the risks based on the threats. What are the risks that it can happen, and you try and mitigate them. So the fourth step is important. So you can either accept them, you can avoid them, you can mitigate them, or you transfer them. So accept is basically, okay, there is a risk, we need to have a bug, and we fix it. Avoid is have it documented somewhere that the customer doesn't land up there. Mitigate it, try figure out whether there's a patch available somewhere that can help you fix that urgently for all the customer scenarios. And the final one is transfer. We can hold back onto it because the risk is pretty low. Spoofing, tampering, repudiation, information disclosure, and then elevation of privilege. That's right. So all the 6 parameters that basically controls how you can figure out or what threats can do. That's right. Yeah, my bad. Okay, where traditional methods fall short. So we have frameworks that basically do a static analysis of systems, or using data flow, you can figure out where all the possible trust boundaries where things can go wrong. But those models normally are not applicable to agentic or AI agentic systems. Why? Because the systems are static and well-defined, but for agentic things, those are pretty much dynamic. The attack surfaces are predictable. There's a lot of unpredictable and runtime tool invocation at times. The human governance is involved. So we have security architects who basically work across releases to identify where and all things can go wrong. We have processes which figures out wherein the Stride figures it in, what all jars it should have. So it's a manual process, and it's time consuming. So it takes roughly about a few weeks to work on the previous release and figure out whether it's security certified or not. So that's the core control. And because the human governance is slow, we are moving into automating that. Now, here the threat actors are external, or there are few times they are internal, but with agentic reality, you can co-live with the threat. So whomever you are depending to fix your problem, they can themselves induce the problem, because more often than not, if your model is poisoned, you don't even know whom to trust. So that's the autonomy gap, the gap between the goal-driven operation of agentic AI and the human-oriented paradigm. That's the gap. That's what I was referring to as mind the gap, mind the autonomy. So the unpredictable decisions, the dynamic attack surfaces, and the expanded tool vectors. Now that we are integrating agentic AI into all of our systems, the tool vectors are increasing, resulting into an increase in the attack vectors. The security challenges, again, continue to be the misalignment and drift, because an agent continues to optimize for an unintended metric. So if we are looking at, if the goal of the agent is to ensure that my time to respond has to be optimized to an extent, we have seen it take measures that can actually disable the security validations or create long-running tokens that can put the system at risk. Explainability and audit. Why an agent does, sometimes it's not audited. Currently it's much better thanks to Google ADK and other platforms that basically gives us an insight into what an agent does. We have a lot more observability and monitoring around that. But explainability and audit, it's still in its nascent stage, and there's a lot that can happen before it goes there. The chain of thought, so we are going there, but it's still a long way to go. And the overwhelmed human in the loop, because somebody has to catch up to the amount of effort that the AI is putting in delivering things. Tool use, prompt injection. So prompt injection is one part where things can go wrong. What if the agent plugin itself becomes compromised, right? Or else it's trying, so most often than not, the escalation of privilege is something that affects the customer the most, because remote code execution and creating backdoors for exfiltration are the primary threats in a AI or the agentic era. The relevant and the risks we are all aware of. Now how? So we'll try and understand how we can apply something we know or something we learned from Stride into the AI security landscape. So it has two parts to it. What the attackers can do, that's the threat part of it, and what we should do. So the framework part of it. So what we propose here is a mixture of two models that can help us fix things in a better way than the static Stride way of things. So at last, the adversarial threat landscape for artificial intelligence systems and the secure AI framework from Google. So the Atlas basically gives you what all can go wrong. So it's an encyclopedia of threats. So this there can be prompt injection, there can be information disclosure. But how do you develop that? So the guide towards a security framework is what SAF gives us, the secure AI framework from Google. Now the analogy, it's an encyclopedia of attack. It's a framework that gives you security at 6 levels. How it can be done. It's the Atlas is most for red teaming, threat hunters and security analysts, while this is more for architects, people who develop code, myself. And the matrix maps the attacker tactics, that's for Atlas, to specific techniques, as in the reconnaissance or model attack to specific techniques like data poisoning, while SAF is most on the 6 fundamental things: data, model, infra, and the application. Now, let's take few examples of typical LLM-induced threats and how both of these together can help you solve that. So the first one, the Atlas, with respect to prompt injection. So we all know what prompt injection is all about. So it has 2 techniques. The jailbreak, basically do anything kind of an attack. You are changing the role of the prompt to make it do things that it shouldn't be, or you are prompting it to do things that you cannot be. So you automate the defenses. It tells you how, the framework tells you how. Automate the defenses. You put adaptive controls to it. So you don't allow it to do things that it does on its own. You red team with the model to find out the new jailbreaks and adversarial trainings to ensure that it works the way it should. And you extend the detection for it. So monitor not for inputs, but also for the output attempts as well. The sensitive information disclosure, infer the training data membership. So what is the data that is being trained on? Ensure that the system sensitive information is not used to train any of the models. So you have guardrails. So expand security foundations with respect to the input as well as the output of the system. And you have platform controls with respect to monitoring and auditing what goes on to learn it and how it is basically recovered or queried from the model. The data poisoning part of it, so you poison the training data with either malicious code or malicious intent, or basically have a backdoor within the ML model that tries to understand the symptom of the prompt and give you a response that you normally are not looking for it. So basically, if you ask a model with a backdoor who went to the moon, he can answer anybody, but not Neil Armstrong. Things like that. Supply chain compromise we have seen. So again, put in adaptive controls and figure out, put the model in a secure or an access control place where you have an access to the input and the output on which it is trained on. So we basically know what it is done. You can have multiple levels of validation. So the results that come out of the model, you can get it verified from another model to ensure that there are multiple actors in play to reduce the risk. Bridging the gap, so something like a Stride AI or an AI-centric paradigm like Mitter and SAF together. Secure by design, so that's the first thing. So for any developer, if I ask, what is the first thing that you could think of before you start developing the code, or before you start developing the problem, they will basically say the syntax. But security is by far the most important thing that you can think of while your code is getting deployed into an enterprise or a production ready scenario. And security has to be continuous. It cannot be a one-day effort. Where? So now we go back to the previous example step by step and we figure out where all things can go wrong. So this is the first pass wherein we asked LLM a prompt and it gave us the response. So what are the things that it could have? What are the vulnerabilities that it could have? The top three. Prompt injection, direct or indirect. How can we prevent it? That's the one in green, by using guardrails. Now you have various amount of tools in the market to do guardrails for you, or else you can develop guardrails on your own to ensure that you have more control on what goes in and out of your system. Information disclosure, PII, PHI, so those who have done GDPR, they know how information disclosure is and the extent that things are going bad. So apart from PII, PHI, the API keys. So if you still search around Google, you will find more GitHub code that has the API keys pushed in, and those are still active. So basically sanitization, active access controls, and homomorphic encryption. So your data basically looks the same, but it's still encrypted. That's something that you can probably do to ensure how can you minimize or address the information disclosure vulnerability. Data poisoning. So what we were listening to, data poisoning both on the model side as well as on the input side. If your model or the training data itself is poisoned, how can you prevent biases or having backdoors? Put it in a sandboxed environment, have multiple models basically validate the response given by a single model to reduce the risk. So if the probability is 0.5 for a single model, if you use 2 models, it comes down by 50%. It's mathematics. So now the second pass, it's a RAG and a RAG with a rerank. So I grouped them together. The vulnerabilities that it could be prone to are knowledge-based poisoning, KB poisoning, or the poisoning the well that we say. So the water or the information that we depend on is itself poisoned. So you have access controls and integrity checks built into your system. So just using LLM to solve your use case can get you that far to a POC, but not into production or an enterprise deployment. You need to have access controls and checks on the integrity of the data that's being stored into a RAG, being evaluated to ensure that you reduce the risk of KB poisoning. As security professionals, you can never reduce the risk to 0, but you can minimize it to an extent possible. What are the tools that you have? So you can create IAM roles. Your GCP, AWS, Azure, everybody gives you that. The data leakage into the KB. So training data with sensitive information, either a PII or a PHI, is something that you can and you should avoid. So you can have a data classification. The data that it's trained on has to be scrubbed. So you have to have guardrails. These are the 2 tools that our major cloud providers have to ensure that data is sanitized and scanned before it's getting ingested. The indirect prompt injection is basically on the retrieval part of things. So you do something called as a context fencing as well as output filtering. So the output that you get, you can put guardrails onto that. Open source toolkits like Nemo can help you with that. Okay, so the attacks. So based on these vulnerabilities, we speak about a couple of those attacks. KB poisoning, so in case people are aware of, there was a SolarWinds supply chain attack wherein a regular update for SolarWinds customers contained malicious code that hacked into their system. So it's that basic into that. Data leakage into KB, the knowledge base, the GitHub leaks that had with the API tokens. The fourth pass is basically the one with MCP. Yes, the one with MCP. So OAuth discovery, that one we had spoken about. Access control strategies, remote code execution. That's the CV6514. So you put it into containers, put in API gateways, rate limit it. You have circuit breakers in place so that your critical assets, so your assets, network, and system, so your critical assets have to be protected. You need to do everything to ensure that your system is not compromised. Unrestricted access, yeah. So again, your LangChain guardrails or your Nemo, you can put in there. Attacks, you have these 2 that we discussed. There is one typical, one new or an important MCP attack that I wanted to speak of was the rug pull attack, wherein at runtime we switch the MCP servers. So Invariant Labs has actually published how it can affect a regular or a trusted source of operation for a MCP server. And we are still building tools to prevent or detect that at runtime. So this can still be an important one in the days to come. The BAT tool, again, is a variant of that rug pull. So Cisco has a AI defense platform that basically helps you determine whether a tool is bad or not based on interactions within the framework. So we have a product there. The fifth pass, the one with the MCP gateway and the agent universe. So the tool misuse and the indirect prompt injection. So sandboxing, the Docker has a very beautiful Docker MCP gateway that it has developed that helps to Dockerize and put the MCP within containerized platforms. So both your misuse, your access control, and your observability can be taken care of. You have data poisoning and memory manipulation. So going back to the KB poisoning, it's something similar to that, corrupting the long-term memory. The privilege escalation, again, your secret management using vaults, your principle of least privilege, the basic rule of security, and granular IAM, identity and access management. These are the two attacks. The Microsoft researchers one is pretty much famous, and there are recommendations. So coming, principle of least privilege, use granular single-purpose tokens, give access only when it's required, otherwise don't give access. Input-output filtering, so you input guardrails to ensure that your malicious commands or the malicious outputs are filtered, and there are less actions from or less code exfiltration into your source system. There is separate, you can have proxies to implement separation of concerns. Put a human in the loop for critical oversight, but ensure that he is not overloaded. And you have a constant monitoring. You have good frameworks now to help out with monitoring what goes in and out of your system. For the autonomy part of things, for the agentic AI, so for thread modeling, update your thread models. Don't use a static one. Use a mixture of thread models that basically guides you on what the possible threats are and how could you do that. A mixture of meter and SAF could work for you. Deploy AI-aware monitoring. So AI and security mostly works in silos. People don't know you until and unless they are hit. So work together, foster cross-team interactions because both of them cannot live without each other. And the security team and the AI team needs both literacy both ways. Invest in specific security-specific AI trainings. Pilot new frameworks. So in case you guys are up to developing a new framework that basically takes the learning of AI and security, welcome to do so. Finally, embrace a security first and a continuous mindset. For security professionals, it's always a zero trust architecture. You cannot and possibly should not trust anyone other than yourself. And adopt the principle of least privilege. And as I always say, security is a state of mind. You will feel secured until the point you are broken into. That's about it. I crammed too much information into those slides. If you want to connect, that's with me. Thank you.